ঠিক আছে।
So let me just remind you, so we were working with the graded rings. And R is a ring. It's gamma graded if you can write this gamma graded, gamma being an abelian group, if you would be able to write R as a direct sum of these subgroups. So these are subgroups of R such that when you multiply these components, you end up in the next one. And an example, so this is a Laurent polynomial ring. So this is a graded ring. So I have to give you the grading here. This is a Z-graded ring. And these are the components. K, X, I are coming from the integers, right? So you can see that if I pick 2, then K, X to the power of 2, this is just one part of these polynomials, and any polynomial is the sum of these monomials, right? Okay, now this is R is a cross product because in each component we needed to have at least one invertible element, and here is the one invertible element. All of these are invertible if K is not 0. Okay. Now, in fact, there are more here. Definition. Did I introduce the graded division ring? I don't think. Okay. So definition. R is called graded division ring if. So previously I said, okay, look at each component, and if you find one invertible element, call it cross product. But what if all the elements are invertible? If they are not 0, imagine all the elements are invertible, such as this one. Okay? Then I call it a graded division ring. If all non-zero homogeneous elements are invertible, i.e. R star alpha is really R alpha if you drop C. Does that make sense? Oh, thank you. Does that make sense to you? So here, anything you pick up here is invertible. Then I call this graded division ring. So why do I call it division ring? So you have to remember that if you have a ring, if this is a ring and it's commutative, meaning that AB is the same as BA for all the A and B, and also any element you pick here which is not 0 as an inverse, then this is what we call it. And then the whole linear algebra is on fields because they behave very well. For example, they have bases. All the modules are free modules. Okay. Now, if it happens that R has all these properties except it's not commutative, then it's called division ring. So R is, well, a division ring if all elements, all non-zero elements, have inverses. Can you give me one example? Do you know this? The famous example of Hamilton. So Look, real numbers, these numbers, if it's not zero, it has an inverse, so this is a field. Complex numbers, a plus bi, right, these are the sets. This is also a field. Each element here you can arrange for an inverse. So this is also a field. But there's a very interesting story. I'm not sure if you heard. Somebody called Hamilton in Ireland tried to come up with the next one because this has dimension 2. Right? So you see that this is a vector space over R of dimension 2. So Hamilton for a long time tried to get the next one which has dimension 3. He wanted to construct a field which has dimension 3 over R. William Hamilton is the most celebrated scientist in Ireland. So if you go there, everybody knows. Even the taxi driver knows Hamilton because he basically was very famous there. And then he tried for a long time to come up with something here. Now it's called Hamilton. That has dimension 3, similar to this. So he started with a plus bi plus some cj and tried to multiply this. Now you have to tell me what is this j to the power of 2, what is ij, you have to tell me all of these, right? So he tried very hard, so ij should be something like this, ji something like this, and it has to have also an inverse. So you have all these constraints. So he couldn't make it. He couldn't come up with any field. And then finally he realized that in fact you cannot construct field of dimension 3, you have to go first of all 1 dimension higher, so it has to be 4-dimensional. So this has to be a plus bi plus cj plus dk, and these are the relation. And then not only that, he realized that it has to have this property, i.e. non-commutative. It has to be non-commutative. So there is no way you can put something here which has all of these assumptions that each element has an inverse, it has to be finite dimensional over these, so you cannot have such a system. It has to be non-commutative. And he was looking for this for a long time, like 15 years. If you go there, you hear the story of this, that he worked for a very long time to come up with this example. And it is very difficult because you can prove, in fact, this is the unique example. So in a very fancy way, the broad group of R has 2 elements here, this and this. So there is only one example of this type over R. So that he was looking for a unique example, so that's why it took such a long time. Anyhow, so this one with this with these little elements, if it's not 0, it has inverses. So this is called a division ring, Hamiltonian division algebra, really, because it's an odd algebra. Okay, now what I did here is that, okay, I don't know if each element, if you write it down, are invertible. All I want is that these components to be invertible. Then I call it graded division ring. And you can prove that if you're working in a graded setting, this behaves very well. In fact, you can develop the whole linear algebra, so graded linear algebra here, i.e. you have modules, the graded modules become graded free, and you have bases. All of the things you can prove on the setting of field and division ring, you can prove it here in a graded setting. Okay, so now let me give you an example of a graded field or graded division ring. So it's a graded division ring. If this happens, if it's at the same time commutative, then it becomes graded field. So maybe I just write it here also further. If a graded division ring is commutative, it is called graded field. And they're very, very nicely behaved. Example, and this example might give you some clue. Look at this one. R is k x to the power of 3, x to the power of negative 3. Can you imagine what I mean by this one? So,
isn't that ring also graded division?
say
Lorentz series polynomials? Lorentz series polynomial?
this is okay. Let's first of all understand what the elements here are. What do I mean by this? So here, the polynomials are coming from x and x inverse. So an element here, it looks like k1 and k1 minus 5 plus k2 x minus 3 plus k3, that's x to the power of 0, x4 x to the power of 10, and so on, right? But it's fine. So all the different powers coming from x and x inverse. Here, what I mean is everything is the multiple of 3. So your polynomials, the power are multiples of 3. So this is inside kx x inverse. Okay? Now, look, if you look at this, stare at this as a ring, this is just isomorphic to this one. There is nothing, right? But now I'm looking at a graded ring. So this is a Z-graded ring. What's the support? So the elements here looks like, well, x minus 6 with some coefficients, kx minus 3, then kx0, which is just k, plus maybe k something else, x3, x6, x18, and so on. So they are all multiples of 3. So this is 3z. Okay. So R is kx3r, the direct sum of kx3i, I coming from z. Okay. So in fact, remember we had a case that if R is gamma graded, that lambda was a subset, then I could construct a subring of this, which is, okay, this is graded, but I want this to be also gamma graded. So I'm just picking up the components coming from here. So if this confuses you, forget that. So now I'm in here. So the polynomials that appears here, they all have power of a multiple of 3. So then the support is 3z. Okay. So it's a z-graded ring, but the support is 3z. Now here are a couple of questions. Is this strongly graded ring? Remember, the strongly graded ring means R alpha, R beta has to be R alpha beta. And we saw this is the case here.
It's cross product.
Okay, so if it's a cross product, then it's stronger graded already, because cross product gives you stronger graded. So let's okay, so the support is 3z. So now, first of all, each component I look at is non-zero component. So you have a k, x, 3 to some power. All of these are invertible because I can multiply immediately with this one. Okay, so each homogeneous element is invertible. So here, each homogeneous element is invertible. So, by definition, R is a graded field. So, this is a graded field. It's commutative. Each of these components, everything is invertible, so it's a graded field. But it's not strongly graded. Because R, so R1, so Kx would not appear here. So R1 is 0. So then R1 times R3 would not go, R2 would not give me R3 because this is 0, this is 0, this is not 0. Right? So this is not strongly graded, but it's a graded field. Of course, then it's not cross product. You'll see this. I mean, I know it's confusing. Sometimes it confuses me too. But it's important for me. You'll see in a second how these appears in the case of Leavitt path algebras. Again, as a ring, this one, as a ring, this one and this one, they are isomorphic. They are the same thing, really. But when you get the grading, as you see here, everything just jumps each time 3 steps. So that's important for me. So now let's do some examples. I just want to look at this. So now let's look at the Hamiltonian division ring. This looks like this. Okay. So I to the power of 2 is -1, like complex numbers, but now you have 3 of them you have to deal with. Going with the other one, no. I think if I write this, then I can also conclude k to the power of 2 is -1 because I have it. Okay. So, as I said, you can write it down, you have to sit there and write it, but that each element, which is not 0, has an inverse. So, Hamiltonian division. In fact, here already, this group is very interesting. So you just drop 0, you get a group. You know, there are still a lot of papers. What is this group? Maybe I just tell you a personal story. So this was the topic I used to do, division rings. So rings which have each non-zero element as an inverse. So division ring, you immediately get a group, and then the interrelation between these algebras and these groups. So for a long time I was doing this, and as I said, this was discovered in Ireland, and I was looking for a job. So the first permanent job I went to Queen's, that's in Ireland, and so you know you have to give a lecture, and everybody is sitting there. So I was thinking, how should I start? You know, how should I start to capture the attentions and so on? And I was doing division ring. So the first thing I said is that, okay, this is the best place to do division rings. And everybody was so happy, and they offered me the job. So anyhow, so this is that. Now, as you see, this is a ring. It's not clear. I mean, if you glance at this, can you write this as graded grid? Can you write this as something plus something plus something? And then when you multiply, it just nicely sits in the other components. Can you do that? Okay. Sometimes it's not really clear at the beginning that you have a graded structure in a ring, but you do have it. Okay. I give you two examples here. I give you two very natural grading on this with different groups. Okay. So first of all, I'm gonna chop this into pieces. I'm gonna give you Z2 times Z2 grading. So I need to give you, let me call this R. I give you R00, R10, R01, and R11. Okay, so I'm gonna break this into these pieces, and here are, for this one, I just look at real numbers. So everything else is zero, then your real numbers, of course, appears here. In fact, real numbers is the center of this string. For R10, I put Ri, and I think you got the idea for the rest. So I just pick up each of these. Okay, so now
you are thinking as R2 plus R2.
That's right. This is a wait. 4 copies of R. 4 copies of R. But then
R2 plus R2. 4 copies of that.
Yes. Well, yeah, but yes. In principle, yes. But then I'm gonna get each of these. And this is a Z now. This is Z2 by Z2 grading, okay? So I have to check a couple of things. First of all, if you give me an element, I can write as a direct sum of these. And this is clear, right? If you give me this, well, A sits in here, B sits in here, C sits in here, and D sits in here. The next thing I have to have this, well, they have to match. I have to have this. Right? So can you check one of them? Can you check that R10, R11, where should this go? The theory tells you where should it go. The theory. R0 and 1 because the arithmetic is done here. So 1 plus 1 is 0, and 0 and 1 is. So you have to check this now. That R10 is elements, so some Ri, and 1 and 1, some element here, some. This should be in here. This should be in Rj. Can we see that? Okay. So R, and this is just Rs Ik. But why is this in here? So Ik, just let me multiply Ik. K is Ij. But this is -1. So this is negative RSG. So you have to take your time, you have to multiply all these components, and it has to end up in the right pieces. So that's good. So this is now a Z2 times Z2 grading with this very sort of canonical components. But I can give you also Z2 grading. Can you guess that? Can you guess how I can chop this into 2 pieces? That I get Z2 grading. So I have to get a C0 plus C1, and these are coming from Z2. And if I give you R plus Ri, First of all, each element here is uniquely written as this sum, and then you have to just check that if you multiply C0 with C1, is in C1, and if you multiply C1 by C1, well, it's in C1 plus 1, 2, but it's in here C0. You need to check this, but everything fits together. So I gave you two different grading, two different partition of HR. And you know, from the beginning it was not obvious really how to do this, but so depending on your situation, if you need, you can just give a grading here, and then this fits into the theory of graded rings. But before I move on, I want to give one more example. Again, this is I really liked this the first time I saw. It was not clear to me. And I need this also in the theory of Leavitt path algebra. Let me see if I can get it right. So now, again, I start with R, a gamma graded ring. And I look at Mn of R, and I want to give this a grading. Okay, so matrix ring over R. So as you know, these are just n by n matrices, and the n by n matrices you fill it with the elements of R. But I want to chop this into pieces. Okay, and here it's really very interesting. So I'm gonna pick a sequence of elements of my group. It's a gamma graded group. Just pick up a sequence, means the order matters. And I'm gonna, based on this sequence, I'm gonna leave a grading here. So as soon as you change this sequence, you're gonna get a different grading. So how am I supposed to do that? So I put the sequence here, meaning that they are important. So the ring itself is just an n of R. But I put it here because I want to give you the components. So what are the components? So I have to give you these components. This is an n by n matrix. The elements are coming from R. But I have to give you these components such that if you have two of these, you end up in the next one. And here are the components. Let me see if I get it right. So here you put lambda 1 minus lambda 1 plus delta 1, lambda 1 minus delta 1 minus delta 1 plus lambda. Is this being recorded? All right. So you put this here, and you wonder why I put this. I know this is 0, but I want to put this so that the pattern we would see in a second how this looks like, this pattern. Delta n by the delta 1 plus lambda. Can you see the pattern here? So R So I have I and J. You're on the I and J. What you put here are coming from this. Okay. So as you see, I don't put all the elements of the matrix here. I'm putting those elements which comes from these components.
I minus ith row, right?
So here, 1 and 2 is delta 2 minus delta 1. So delta J minus delta 1.
But you have written the first column as the first row. So there should be a change.
That's R minus J. Yeah, you're right. I minus J. That's right. That's correct. Thank you. All right. So
Just
this is
change the first row.
why here delta 1. This is correct. I think delta 2 minus delta 1, delta n minus
1
delta
minus
1.
delta 1 minus delta 2.
This is delta. I screwed up here.
This is
Delta 1 minus delta 2 or delta 2 minus delta 2 plus gamma or delta n minus delta 2 plus gamma. Okay. So this should be,
yeah.
Sorry, I think this is
Yeah, then this should be delta j minus delta.
then I have delta
Yeah.
j minus delta.
Yeah.
The other way also works. It doesn't matter, right? That's being left or right modulus. The other one also works, but anyhow, I have to write it correctly. So these are the components. So the elements here you just pick up from this bit of R and you plug here. So this is the components. Then it's a very, very nice exercise to get one of these, multiply with the other one, and then as you are multiplying rows and columns, you see things would cancel out nicely and end up here. So I encourage you to do one of them. And you see how nicely things would cancel out and you end up in the next one. So therefore, this is a gamma graded ring. And I need this for Leavitt algebra. But let me give you an example. I hope I don't make a mistake when I'm calculating this. So suppose now, example, R is a graded ring, gamma graded ring, or even Z graded ring. Concentrated in degrees here. So meaning R0 is the whole R, everywhere else is 0. Okay. All of the R is in R0. Okay. Now, look at this one here, M3R011. This is a sequence of elements from Z, and I want to get this. This is a ring, this is a Z-graded ring. But I want to consider, now calculate A0. So let me calculate A0. So you have just to plug this in here. So first of all, I plug this in here and then decide what are these. So, okay, so this is R0. This is R1. R1. I think this is R negative 1. This is 0. 0. I think this is what you get. Just plug in there. Hopefully what I wrote here is correct. So this is 0, this is this bit here. This is this lambda. Alright, so now I go back and I see what are the values here. R0 is the whole ring R, and R1 is 0, 0. Let me just, and then I get back. So R negative 1. Again, R negative 1, everything concentrated in 0. So this is what I get. So the 0 component has this arrangement. And if I want to stare at this a little bit, I see this has to be a ring. Remember, the 0 component is a ring. So this is a ring. And this ring is isomorphic really to R times 2 copies of R. Because when you're multiplying this, you're multiplying these entries and then this bit. So this is, so not bad, huh? From here, the zero components of this is this ring. And you change this, as I said, I really like this. You change this arrangement will change. And this is really the part that it gives you a lot of power, because if you don't have grading, all you have is just mn of r, the whole block of mn of r. But if you have grading, you can filter through. And let me give you one more example. You have seen this, but I need to write it for you.
How will it look like in the, if you take the sequence to be 101?
101, 101, go. Okay. You would get a little bit.
No, my question
yes.
is that without computing, we can compute the answer.
Well, in this situation you can, because there is a theory that, okay, if I give you a permutation of this, they are isomorphic. So if you just shuffle this, they are isomorphic. Although maybe R and R appears here, right? This block appears here and R appears here, right? So if you just shuffle this, permute this, you get to the same thing. But then again, if I put these two, then things might change.
Sir? So is there another way to look at it and say that it is graded rather than working on these DX and decomposition?
One more time.
Is there another way to look at it and say that it is graded rather than working on this decomposition, I mean this DX and decomposition or any kind of program? It's a say that it is a graded.
Okay. First of all, let me say something and see if this answers your questions. So I want to make this a graded ring. Okay? I want to make this a graded ring.
This is interesting. Can you repeat the question?
I'm asking that whether we can look at a ring and say that it is graded other than using this direction thing by studying some.
Is there another way to characterize graded rings?
What should be your definition? Decomposition and definition. What should be the definition of graded? That is definition.
So, look, yes, I mean, I give you this one, and you're asking, can you make this a graded ring? Okay, so let me at least tell you this. I look at this matrix ring, and here is one way to make it a graded ring, right? You change this, and you get all kind of grading. I think they call this good grading in some literature. But there are a lot of gradings you can put on this, which are not coming from here. So that's also, again, a research theme. How differently you can put gradings here. Can you describe all the gradings you can put in here? All the, say, Z grading. All the Z grading that you can put on this ring. And I've seen papers that they, I think if I'm not mistaken, they do for this, because it becomes very complicated. You know, exhaust all the gradings that you can put on this. Okay, so now
Can we say when a ring doesn't have any grading except the trivial grading? A ring does not have any other grading except the trivial grading.
Yeah, probably, I'm sure you can do that, maybe say that you cannot write it as a.
So that problem you said where we find out how many ways you can grade a ring, is that perhaps a combinatorial problem more than an algebraic one?
Well, your question is very general. I'm sure there are cases that you can use computer to count.
Combinatorial.
Combinatorial.
Yes.
Again, could be, because it's a very general question. Maybe in certain cases, in certain rings, combinatorics come into play. In certain rings, it doesn't. So it is possible, but it depends on your setting, your ring.
The 2, 3 matrix 18. The 2, 3 element.
Here,
The second row, third column element.
here,
That should be Ri. Where should be R?
Second to third column.
Third column.
3 minus 2, 0.
1
minus 2,
Oh,
1 minus
R1.
1.
No, so that would be R1. But
No,
R1
R0.
is
R0.
1 minus
There
1.
is 0, 1, 1.
2, 3.
Sequence is 0,
Two,
1,
three,
1.
Yes, right. Oh, sorry. That's
yeah, if you plug into that formula, that should be yours.
okay.
I'm pretty sure this cannot be 0 because then it's not a ring.
No,
But
yeah.
this has to be a ring by view. Alright, and the last example of this kind is, okay, I'm giving you this one with this grading. I just plug here this because I could just plug any number I want. Right, I could. And then, remember the example we talked about that you do this arrangement, here you put R, everywhere else 0, and then you just put below diagonal R, everywhere else 0, and you go like this. We start with this example. This is here. So this one covers this very nice arrangement of the.
Sir, can you please write down the formula for the ijth element of the matrix?
All right, so this should come from R. This is for the lambda one. You fill it with this formula.
Membrane component.
Which is 0,
Ij is using J minus I.
Okay, so then, so these are rings. Let me just mention briefly. So you go through the whole ring theory, and then you want to develop everything with a graded version of it. So the next thing is that the ideals. So let me just mention this because I need that also when I'm defining Leavitt path algebra. So imagine that R is a gamma graded. And just get an ideal of R. Then when is this a gamma graded ideal? It's exactly as before if you can write this into these pieces, right? So then I is called gamma graded ideal. If this is one way to put it, there are a couple of different ways. This is the same as the direct sum of I intersection R alpha. If you would be able to write it this way. So, this is an ideal. Of course, these are elements of I, so these are all sitting inside I, but I'm forcing with this definition that each element of I, you can write it as a direct sum of homogeneous element, i.e., if you give me an x in I know for a fact that I can write x as x1 plus x2 as a sum of a homogeneous element. I can do that because R is gamma graded, so each element you can write as a direct sum of homogeneous. But I want these little ones also all be in I. So if this happens, so everything is happening inside I now, then I call I a gamma graded ideal. So if you do that, then immediately you can see that this is a gamma graded ring also. I know this quotient is defined because I is an ideal, but I have to give you these components, and this is what I put here, where each of these are I, maybe I just write here, I plus R coming from R half. So these are the bits that I give. So now maybe you want to think, if I don't have this property, well, I is an ideal, this is okay. So I write it this way, and I'm defining this. You have to have this property so that this will be well defined. Okay, you want to think about this a little bit. I need to have this property that each element of X you can write as sums inside I, so that you get this to be well defined. Okay, now that's that. Now let me move on to the graded module theory. So bear with me another 15 minutes so that I cover the theory and we go to more interesting stuff. So now, as usual, R is a gamma graded ring. Now I'm going to work with modules. So imagine M is a right R module. So this means that really there is an action of R on M in a very nice and compatible way. Then I say M is also a gamma graded module. If the same business, that I can write M as a direct sum of these components, such that, can you guess what I want to write here?
This is M alpha plus beta.
Say it again.
M of alpha plus beta.
That's exactly right. Because I know that when you multiply R with M, it's inside M, but I want to be, everything in this component matches nicely. Okay, so that's that. And the next thing is that if M and N are gamma graded module, and phi from M to N is an R homomorphism, then it's called gamma homomorphism, gamma graded homomorphism. If, can you guess what I want to write? So I know that, I'm pushing elements of N inside N in general, but now M, I can have these components here. I have the components here. I want this to respect that. So what should I write here? So I pick M alpha. I push this inside N. Where do you think I should land? In N alpha. So everything is very natural, very canonical, the way that we can write. So then this is called gamma homomorphism. And then right away now the whole theory becomes about these categories. So now it's gamma graded. Then I have this category. This is a category of graded, and I write this that I'm acting from right, so category of graded right R. Graded right R module with, so the category means I have to give you the objects. These are my objects, all the graded modules. So with morphisms, graded homomorphisms. Okay, so I just collect all the graded modules here. Because R is a ring, well, I have also the category of all modules. Okay. In fact, there is a forgetful functor you can put in here that if I give you a module, if it's graded, if I give you a module, it's graded. But, well, before you go here, it's a module anyway. So I just put this forget and that extra structure, and it's called a forgetful functor. Actually, I don't know why in some literature call it U. So a forgetful functor, forget the grading. So you have now a functor from the category of graded R modules to the category of modules, and you have another functor now to, what do you think I can put here? What other ring involved?
R0.
R0. So get the M, get the zero component, you can immediately prove, because of this condition, that I know R0 is a ring, and I know R0 when acts on M0 ends up in M0. So this becomes an R0 module. So the whole theory of graded rings, you are concentrating on the interaction between these three categories. As soon as you get a gamma graded ring, you have three categories. And the usual thing, how can you lift properties from one to another?
Isn't every component an R0 module?
Tell me again.
Isn't every component R0 module?
Every component is an R0 module, that's true.
So we can just define M to M0, right? Because is this map well defined? Because we can we talk, there might be different gradings for same R with different M0s. So I'm not sure what I'm
What do you mean?
trying to twist it out.
I mean, of course you can do this, as you said. I just send it to a fixed alpha. That gives you another functor. Okay, that I can do also. But really, this is just means, okay, I'll get here, but this means just, first of all, I shift the modules. You'll see in a second what I mean by shift, and then I forget I get the zero of that. But let me just get there. But you're right, so these are also R modules. So now the next step is the most important thing. So the most, for me at least, the most important concept called the shift or suspension of a module. And that makes things different than the usual group module theory. So what does this mean? So imagine that M is a graded R module. So therefore M is this direction, right? And as you saw, I always focus on these components. Okay. So if I pick alpha, I get this M alpha. If I pick beta, I get M beta. Now the shift of M, maybe I call it the beta shift of M, and I write it this way, is also an R module, is a graded module, graded R module. So now I have to give you the components here. So I have to give you this component, right? So this is my new gadget, M beta. Now I have to give you this component here is M beta plus M. So I'm kind of shifting everything with this much. Okay? So this is called the shift of M or suspension. Maybe this comes from topology, but maybe I just dropped it. The shift of M. So I always have a nice chart that might show you what I mean by the shift. And that tells you why these graded rings are good when you want to capture dynamics. So imagine M is a Z-graded module. So this is your M. This is degree 0, degree 1, degree 2, degree 3, negative 1, negative 2, negative 3. So here sits M0, M1, M2, M negative 1, and so on. Okay. Can you tell me now the components of M1? Now you have to stare at this definition here. Tell me the component of M1. So M1, 0 is what? It's 1 plus 0 is M1. This becomes M0 because M1, negative 1 is M0. Okay, and then this one becomes M2 because, yeah, so M1, 1 is M2 and this 2 becomes M2. Let's do this one here, M2. What's the component of 0 of M2?
M2.
Is M2, right? You follow me here, M2. What's the component M2 negative 1? M2 with negative 1. You just add them, you get M1. And this is M0 and this is M3. And let me just do this so that you see the movement. So you see what happened? I really created a dynamic. If this is 1 second moving, so everything is clicking to the right, oops, to the left, right? So that's why they say the graded ring, I mean, I'm working in algebra, it's a discrete thing, but if there is a chance to capture dynamic, maybe the graded ring is a good setting because I have these movements. So that immediately, this shift, that shift immediately gives you a functor from here to here. I send M to M alpha. So this is a functor. I give you the objects. You just shift it by alpha, all of them. And this is, in fact, an isomorphism. It's an isomorphism functor. Because you can do the negative alpha and you are back, right? So this is really an isomorphism. Now, if I'm working with two rings, then of course, the next thing is that I want to compare GR of R and GR of S. I always want to compare the functors. If you give me two rings, I want to compare, the categories. Okay? Now, when I'm in this setting, I really want this to respect the shift. So I really want F T alpha would be as T alpha F. So what does that mean? Let me just unpack this. So F is called graded functor if this happens. What does that mean? Okay, just plug elements or objects here. So I get F T alpha M. With this one, you're shifting with alpha, so I get F of M alpha. And then here, I have F of M here, and then I shift this with alpha. And I want this to be the same. Can you see the difference here? One of them is this module, then I push it here. The other is that I push the module first and then shift. Now, be very careful here. I really want in the theory these to be exactly the same. That's why I call it graded functor. I mean, in algebra, when you say same, you mean isomorphism, right? These two would be isomorphism. But I don't want isomorphism. I want exactly to be the same. One reason is that a lot of things would not work because when this is an isomorphism, you might have a million different isomorphisms here, and with the next one, again, you have a million different isomorphisms. When you compose, you don't know which one you are choosing. So the theorems would not work because you have options and so on. Here, I really want to be, so shift, push it here should be the same as push it here and then shift. Exact same thing. Called graded functor. And let me write down one of the very powerful theorems here. Theorem. I would write very surprising. Okay, so R and S are gamma graded ring. And imagine you have an equivalent functor here. So that means not only there is a functor going back, the composition is isomorphic to one. So these are equivalent. Then I had also this very big sort of mother of all these rings. Of course, here you're working with graded modules. So this is a subcategory of this. With forgetful functor. Right? So all these are sitting here. All these are sitting here. But here, you might have a lot more modules. These are modules that you cannot break into pieces. So you have a lot more. Also here, you have a lot more. But amazingly, if you have an isomorphism on your equivalence on this level, you can lift it up to an equivalence on this level. This is absolutely not clear to me because these are much, much bigger. But you can prove that's the case. So if you have an equivalent here, then existent equivalent here, maybe I call it even 5.
Is it due to Dadu? Is it due to Dadu? Dadu proved this? Never is the Dadu. Is this proved by Dadu?
This is proved, no, this is not proved by date. This is, no, with date you mean?
Date.
No. Date have done with R mod R0.
How?
And if this is strongly graded. Yeah.
Phi is an isomorphism.
Phi is an equivalent of categories. Yeah, that's right. So here also phi equivalent. So this is one of the things that the smaller categories sort of can determine the behavior of the bigger.
So every equivalent isomorphism from one category of graded R modules can be lifted to
The whole thing. And here, this is also very astonishing that this is not Z or finite group. This works for any group. Now you can. Somebody asked me about generalization. I don't know if you change this to semi-group, groupoid, or so on. You have to trace the whole proof and see if it works here for other kind of gradings. I don't know. You have to go through it.
So it's a good motivation for studying graded structures. It's a good motivation for studying graded structures.
Yeah, sure. Sitting there determining the whole thing. Also, yes, so you might have an equivalence here, and it doesn't give you an equivalence here, perhaps.
So what is the reference on this?
This is also in that book, you can see. In the blue.
Oh, in your book?
Yeah, it's in there. The proof is in there. But I would write here, can you write this for other kind of gamma? Because if you relax this, then here, remember this one, alpha, you go back and forth. If this has no negative, I mean, it doesn't have an inverse, then you might not go back.
It will work for groupoid but not for semi-groups.
Yeah, for semi-groups probably you cannot go back. I don't know if that plays a role here or not, so you have to go through the proofs.
So when we talk about category of graded anomalies for a fixed abelian group.
Yeah, that's right. Okay. Yes.
So if we show an equivalent in any abelian group, an equivalent isomorphism, that can be lifted to whole modules, to category of all modules, let's say.
That's right.
So if we can show some property in some simple gradings and some equivalence, then we can study it in.
I see. Yeah, I think that's what you're saying is correct. So it doesn't depend on this. As soon as you can show that, so remember from the quaternions, I could do Z2 and I could do Z2 times Z2. In the situation that I have this, maybe Z2 would be easier, so I fix Z2, I can show, if I can show there's an equivalent, then the whole thing is clear. Maybe it's not there, maybe it's here, so then I fix that, maybe I can do it here, then I just... Okay, and maybe I'll finish by introducing the monoids now assigned to these, and then next time I specialize to Leavitt path algebras. So now, if you're working here, this is the category of modules, and you can define all kinds of properties of these modules based on this language of the category. I can, as soon as you get one of those, I can just translate and do the same thing in here. Okay. For example, you can define projective modules here in this category. Now I change it here, I get a graded projective module. So let me just define one of them. So definition: R is a ring. P is an R module, left or right. Then P is called projective module, projective R module. If you have this situation, so these are N and M are R modules. And this means that this is surjective. Then if you have a map here from P which goes to M, then you can lift it such that this is commutative. So if F and G are given, so because this is surjective, you can think of this rather it's bigger than N because it's covering the whole N. So if P goes to M, then I can lift it up and say P goes to L, and this is commutative. This is called projective. Now you can immediately just imitate this and tell me the definition of a graded projective. So can you do that? R is a gamma graded. These are called graded projective. If you have exact same thing now, these are graded. F and G also are graded. So everything is graded, then I call this P graded projective. But now you have, as soon as you have one graded projective, you can shift, and you have a lot of them.
How do you formulate in terms of home function? How do you formulate in terms of home function?
Home functor.
Home P dash is exact. So in case of graded module,
It's still exact for projective modules.
yes.
I mean, the exactness doesn't have to do with the projectiveness,
Yes.
but with the grading. So as soon as it's projective, well, it's exact. If it's graded projective, it's already projective and it's good. So let me just write this down, theorem. This happens only for this case. So R is gamma graded, then P is graded projective if and only if P is graded and projective. Let's see if we understand this.
The question is localization of a graded ring or graded ring. Localization of a graded ring.
You can do all of those, yeah. Graded localization. You know, whatever you think it can be done. Most of them also quite natural. But let's look at this one. This is a bit confusing. So P is a graded projective. See if you see this little. It's okay. P is graded projective. It means that P sits in here and it fills the diagram. But when I do this, N, M are graded, and these are graded homomorphism. Okay. Now the theory says P is graded projective. It implies that P is projective, and this is not clear to me. Why? Because if I give you this, and N and M are not N and M are not graded, and you put P here, why P lifts here? P lifts if N and M are graded, right? But this says that P is also projective. So for anything else, also it lifts. This is not clear to me at all, right? So this way is not clear to me. The other way also, let me see if I can see that. So now imagine P is graded and P is projective. So P is graded and is projective. I want to say it's graded projective, namely it sits here. Okay. So look, you give me this. I want to prove it's graded projective. You give me this. You tell me this is graded, these are also graded, okay? And you tell me this P is projective. Then there is a map. Why is this one should be graded? Because I'm working with just projective. So I have a map which commutes, but there is no guarantee this is graded, because you can have many, many different maps. So this way also it's not clear to me. One of those theorems that usually theorems in one way it's easier to prove. These, both of them are not clear. So you have to prove it. I didn't define this, but let me just put this that it's not always like that. It's not always graded projective is graded and projective. So you have a notion of a graded free. So graded free. This is not the case that it implies P is graded and free. This is not the case. So it's not always obvious. Okay. Let me define the monoid I'm interested in, and then we continue next time with the Leavitt path algebras. I'm getting the questions that we can think about. All right, so then if you remember from the first presentation, if R is a ring, then you can define a monoid. These are the isomorphism classes of finitely generated projective R module. Okay, example. If R is a field, so let's understand this. I'm getting projective modules. Those are finite generated, and this one means I just look at every one which are isomorphic to each other. I just pick all of them at the same time. So that maybe represents a lot of them. So that's one class. The other class and so on. And then, as usual, when I'm adding, I just add with direct sum. You can quickly see that if P and Q are projective, this is projective, so this makes sense. If you give me two different ones which are isomorphic, they are isomorphic here, so this is well defined. Now, let's calculate again. If R is a field, immediately you can see that any module is free over fields. Okay? So the free modules are of this form. Okay. Also, remember that because you are working in linear algebra now, this is not going to happen if n and O are different. So that means this is nothing but n. One way to measure this is not completely true is that if I give you a ring, more you go away from n, more you are going away from linear algebra. So the whole linear algebra that you have, very nicely, you have equations, you can solve and all of that, that works over a field. More you go away from n, more you cannot do linear algebra. For example, we saw that L2 gives you just two elements. It's very, very far from n. So this algebra is very far. Now, you know what I want to do. I want to give you the graded version of this. And this is the gadget I'm going to concentrate throughout the whole thing. So now R is a gamma graded ring. So can you write this down? Can you tell me what I should write here? I get all of these, but then I just get graded, finitely generated, graded, projective R module. That's it. That's the difference. Read this. Now, that gives you a monoid. But this monoid comes with a bit more structure, and that makes it very strong. That this is much more richer than this one. The extra structure is that there is an action of gamma on this. How? So I have to tell you, if you give me an alpha and you give me an element here, this is how I write it, okay? Alpha on the top. I just push this with alpha. Remember the notion of shifting? It makes absolute sense to me. If you are pushing alpha, if I want to push this element, just shift it. So that makes this a gamma monoid. So when I'm talking about this monoid, I always talk about this with this extra gamma structure. Alright, so next time I do some calculation just for maybe field again, so even you field here. I'm going to calculate the VGR of field. You see that it is much, much bigger and it has more information. And then, as I said, I specialize to Leavitt path algebras, and I go. So eventually, I want to, so that you know where I'm going at the very end, probably the last page of what I would say is this conjecture. That if you have two graphs, finite graphs, then, yeah, so you have two algebras, two Leavitt path algebras. And you wonder when they are the same, right? When two Leavitt path algebras are the same. And the conjecture says that if these are the same, if these monoids are the same, and well, one of the elements here is LE itself, right? So for any, look here, one of the projective modular is R. R is a projective modular by itself. So one of the elements is this one. So now, if you have an isomorphism which sends this to this, then you get an isomorphism. And if you have an isomorphism, this bit is very easy. You see an isomorphism at the level of a molecule. So this is the conjecture, so I'm going towards that. This is still open. And as I'm going towards this, don't be scared of this thing. I know this is a bit involved. You have these Leavitt path algebras, and then you have these that you have no control over these projective modules. So this gadget is very scary at the way it looks like it. But you will see in a second that this is, I can define this as just a monoid attached to this graph. So I forget everything about this structure of algebra, everything about this projective. So I forget completely this. I can define a monoid associated with this graph. And that you can do, and every undergrad would understand this monoid. So it just becomes, if these two monoids are isomorphic, then the Leavitt path algebras are isomorphic. So these are called the talented monoid of a graph. All right, so let me stop here, and then the last session would be about the Leavitt path algebras and calculation of all of these and this conjecture. Thank you.